Hello, and thank you for joining me today. My name is David Camacho, and today I'm going to share a little bit about transformers and how powerful these large language models are, and at the end of the day, how these neural networks have shaped the world in which we find ourselves today, and how they have really expanded the NLP realm. So, just a quick agenda for today. We're going to speak a little bit about the history, where they come from, when were they first discovered. Then we're going to do a technical deep dive into the different components of transformers and the component blocks and the attention mechanism, which is the heart of the transformer. Then we're going to briefly talk a little bit about the applications of these transformers and where they are currently found. And finally, we'll close with a conclusion and wrap everything that we have basically said previous to that. So, without further ado, the history of the transformer began in 2017 with a paper that has become very recognized, and the title of this paper was Attention is All You Need. And this paper was created by a couple of researchers from the Google Brain team. And the main motive for the transformers being created was to be able to generate or to translate a piece of text from one language to another. Now, at the end of the day, transformers stem from RNN, and so that is just a recurring neural network. And they follow that same architecture, which means that they follow the encoder-decoder principle. So that was already, pretty much available. However, there were some shortcomings with RNNs. The difference between, or one of the differences between the RNN and the transformer was that the transformer was no longer relying on recurrence. It was going to rely specifically on the attention mechanism. And we'll speak a little bit more about that in just a second. But the two main reasons why the transformers were actually created and why they were a little more favored in terms of the RNNs, at least in this paper, the way that it's described, is number one, because of the difference of being able to compute in parallel. So with RNNs, an input or a sequence an input was able to be computed only in a sequential manner. And so one of the pitfalls about this was that it wasn't able to take advantage of the GPUs, of all of the GPUs. And so with the transformer, we were able to take a piece of input, we were able to take a piece of text, and utilize the GPUs available and therefore compute in parallel. So that just saved us so much time. It reduced training time and many other things. The second reason is the distance and significance aspect. And so one of the problems with RNNs is that as a piece of text got larger, the relationship between words was actually lost. So let's say that you have a very important word at the very beginning, and then you mention that same word or a very related word to that all the way at the bottom, and your piece of text is pretty big, then this is where the RNN was unable or had a harder time to make that distinction or that relationship. With transformers, because everything or an input or a piece of text is taken in as a set rather than in a sequential manner, then that is not lost. So those are just two main reasons why the researchers from the Google AI team, for the Google Brain team, decided to expand on this and create this and elaborate a little bit more on the technicality of it. But you know what? Let's go ahead and speak a little bit more about the component breakdown and what actually is a transformer and what makes up the transformer block. So there are a lot of key pieces within the transformer block. We have embeddings, we have the encoder, the decoder, the attention mechanism, the feed-forward network, the layer normalization, and positional encoding. And so the embeddings, words or tokens were first converted into numerical representations, and so these are what are known as embeddings. And I mean, words are not the only thing that can be used as input. They can be also, images, or they can be sound. And so in this case, this input would be tokenized and then be converted into embeddings. And so these are just numerical representations. So if you have a word, you would take the token of that word, and you would tokenize it, and perhaps every letter would be a token. If you have an image, then you would take smaller pixels, take pixels and make them into their own embeddings. And with sounds, you would perhaps have short chunks of sound waves. For the encoder, think of it as like a translator that reads and understands the input text, breaking it down into meaningful patterns. The decoder takes the encoder's understanding and turns it into a response or prediction, such as translating or generating text. Now, the attention mechanism is the heart of the transformer block, and so the attention mechanism helps the transformer focus on the most important words in the input, like highlighting key ideas in a book. At least that's the way that I like to think about it. Then we have the feed-forward network layer, and so this is like a mini calculator that processes each word individually to refine its meaning. The layer normalization ensures that everything stays balanced and smooth, like adjusting the volume to the perfect level. So you can lower the volume, you can increase it, and it's like a knob, if you will. And then finally, we have the positional encoding. And so that gives the model a sense of word order, so it knows the difference between the cat chased the dog and the dog chased the cat. And we'll talk a little bit more about this, but as we know, the RNNs are able to have that sequential pattern, but because everything is absorbed as a set with the transformer, that piece is somewhat lost. So positional encoding helps with that. So let's talk first about the encoder, and you can see a representation on the right hand side, or at least the representation that was written in the 2017 paper. For this specific paper, there were 6 identical layers. For other language models, large language models, like GPT or like BERT, they may have different layers, but specifically for this transformer that was spoken about in the paper, you have 6 identical layers. You have 2 sublayers for each layer. You have the multi-head self-attention mechanism, and so this helps the model focus on the most important words in the input by looking at all the words in the sentences simultaneously. The multi-head gives it multiple perspectives, so cat and chased versus cat and dog. And then you have the feed-forward network within the encoder. And so this processes each word's embedding independently to gain more meaning, giving each word its own mini transformation to capture deeper features or patterns. Pay attention to how in both the multi-head self-attention mechanism and the feed-forward network layer, a layer normalization is followed right after both components, and that is depicted here as the add-in norm. So these help stabilize and improve training by combining outputs from sublayers with the original input, so the residual connections, and normalizing them. We also have the decoder, which in this paper as well has 6 identical layers and 2 sublayers for each layer. You have the masked multi-head self-attention mechanism, and so this allows the decoder to focus on the previous outputs it has generated so far, while preventing it from looking ahead, so hence masking future positions. You have the multi-head self-attention over the encoder's output, and so this enables the decoder to focus on relevant parts of the encoder's output, incorporating the context of the input sequence. So that's just one part the encoder that is going into the decoder. Next, you again have the feed-forward network layer, which applies a fully connected network to each position, refining the decoder's representation of that data. And for all three components here, you have the normalization layer, which is again depicted as at a norm, and it's applied after every component above, as we can see on the top right-hand side. Next, you do have the attention mechanism, which, as we've mentioned, is the heart of the transformer. And this is a scaled dot product of the three vectors. We're able to see the formula on the right-hand side. And this is just the formula for simplistic purposes. But we have the query, which is denoted as Q, which represents the current word or token for which attention is being calculated. You have the key, which is denoted as K, and that acts as an identifier to help determine which parts of the sequence are relevant to the query. And then you have the value denoted as V, which contains the actual information that will be weighted and passed to the next layer. So a little bit more about the attention mechanism continued, and I'm sorry for that. So on the top right, on the right-hand side, you're able to see the representation of this actual workflow. And at the very bottom, you have Q and K, so the query and the key, and you perform matrix multiplication. So it's the dot product between Q and K, and that calculates the relevance between the query and other tokens. Next, it goes up to the scaling portion. And so that just basically means that dividing by the square root of d sub k prevents large values that could skew the softmax results. After that, an optional masking is applied, which can be used in the decoder to prevent looking ahead during generation. Then you have the softmax layer, which converts the relevance scores into probabilities, which determine how much focus on each token should receive. Finally, you have the final matrix multiplication, which is at the top in purple, and that is the weighted sum whenever we combine the probabilities with the values vectors to produce the output. So once all of that is said and done, that is a singular layer, if you will, once one of those iterations happens. However, we have the ability of the multi-head attention, and so that just consists of H blocks of attention stacked in parallel. And so this is where we said that it has an advantage, that a transformer would have an advantage over a recurrent neural network because of the ability to stack all of these blocks in parallel. So this allows each word in a sequence to focus on different words in the same sequence, helping the model understand relationships and dependencies between words, such as the balloon popped because it was poked by a needle. The contextual reference here ties balloon and it to recognize that these are similar, or that they are speaking about the same thing. Next, we have the feed-forward network. And so this is an attention sublayer in encoder and decoder that is followed by a fully connected feed-forward layer. So the attention layer is within the encoder and the decoder, and then it goes into the feed-forward network. What happens is it's applied to each position separately, which consists of two linear transformations with a ReLU activation in between. And we can see again that formula on the right-hand side. And so W1 is depicted as the weight matrix for the first linear transformation. B1 is depicted as the bias term for the first transformation. The ReLU introduces non-linearity by applying the max function. And then W2 and B2 are the weight matrix and bias term for the second transformation. It's important to know that while the self-attention mechanism focuses on capturing relationships between tokens, the FFN, or the feed-forward network, refines the representation of each token. Next, we have positional encoding, and because transformers treat input as a set rather than a sequence, inherent order information is lost. unlike in RNNs. Positional embedding is added to the input embedding to give the model info about the position of token in sequence. And so this is one of the things that I was mentioning during the history of transformers, that because everything is treated as a set, or at least the input is treated as a set, so that relevance is not lost. Now the position is in a gray area, so this is a reason for that positional encoding, to know and help to identify the positions at the end of the day for each token. So that is the explanation of the component breakdowns. And let's talk a little bit about the applications. So, from 2017 up until 2014, there have been, so many advancements, and we've all heard of BERT, which comes from Google. We've heard of GPT, and we've heard of T5, but I think one of the most famous or more popular companies have been OpenAI, which has come up with ChatGPT. And at the end of the day, the explanation for ChatGPT, or GPT in general, is that the G stands for generative, which means that it has the creativity to generate original text as it was written by a real person. It can absorb input and then generate new text. The pre-trained, or the P stands for pre-trained, which means that it is trained with vast amount of text from books, articles, websites, and more, and it can conduct, generalization or summaries. But finally, the transformer is what ties all of this together. And so this is the architecture that we just mentioned that helps it to understand the connections between words, context, and even emotions. So it's a very powerful tool, a very powerful large language model that allows us to summarize, to create images, to create sound waves, and just to receive a whole lot of input and create something that is very human-like and easy to understand. So in conclusion, what we spoke about today was the following. We spoke about the history and how its first discovery was found in a research paper by the Google Brain team, and it was written in 2017. And we spoke a little bit about the differences of what was already existing, which was the RNNs, the recurrent neural network, and how it came from a large language model, and why they decided to create the transformer, and some of the advantages over the RNNs. We spoke a little bit about the components and the different breakdowns and where they find themselves along the path. And then finally, we spoke a little bit about the applications of the transformers and where they're currently being used. And I presume that this is something that is going to continue to grow, and there is going to be different variations of this, just like there already is. One of the things that we mentioned was it having multiple, mentioning how in the paper the decoder and the encoder each have 6 layers, but something like BERT or GPT may have even more layers. It just depends on the different type of application that it was used for. But at the end of the day, transformers are something that have definitely reshaped the world in a tremendous amount over these past 7 years. And I think that it's something that we must adjust to, because there's no telling what can come next, and how this advancement can continue to shape the future. Here are my references, and if you have any questions, please do not hesitate to reach out to me. I'd love to collaborate and speak a little bit more about this. Thank you, and have a wonderful day.